Welcome back. I realize it's been a minute since the frame video, but a lot more planning has gone into the project, making this installment of the video series a bit more involved. And Roku isn't my only project right now. In this video, we are going to go over the power and avionics system design. If you haven't seen the first two videos in the Roku series, there's a link to the playlist in the description. We're going to dive quite a bit deeper in this video, so buckle up. See you in 27 seconds. My name is Ben Steinman, and I started Rotor Visual back in 2015 to focus on developing and operating commercial unmanned aerial systems, or drones. In late 2019, it felt like it was time to go big, and I began designing a new aircraft capable of lifting pretty much any camera system. So join me on this journey as I document the process of building a massive drone. It really goes without saying, there's a lot going on when it comes to the power and control systems on a multi-rotor aircraft. Like we went over in the previous video about the airframe, making the motor propeller selection locked in several aspects of the design and actually made it easier to make decisions about most every other aspect of the aircraft. Since the Hobbywing X-Rotor Pro X8 motor ESC prop combo is a 12S system, it also locked in the battery and power distribution voltage and electrical current requirements, therefore making the selection of those components fairly straightforward as well. However, not only do you have to power the propulsion systems, but also avionics and what could amount to several payload options that often have varying power requirements. Flight controllers, positioning, and telemetry avionics are heavy subjects, but fortunately, there are only a few options that are really viable to be considered for a large UAS like Roku. It's usually best practice to select a flight control system that is tried and true unless there is time and budget to develop one from the ground up. Once again, this is a prototype, so off the shelf makes sense in this case. I evaluated the features of the DJI A3 control system. It's a great professional flight controller, but with the recent evolution of the Ardupilot software and the introduction of pro-level hardware from Hex Technology in the form of the Cube Pilot system, I had to take a closer look at those advancements. Having used a few versions of Ardupilot on Pixhawk hardware over the years, it quickly became very apparent that leaps and bounds had been made in the advancement of their ecosystem. Cube Pilot has an amazing set of features as far as processing power, redundancy, and connectivity options are concerned, making it an easy choice for this project. They even put together a pretty comprehensive example integration diagram that shows just how versatile the Cube Pilot ecosystem is. Telemetry is very important for safely operating an uncrewed aircraft like this. Since the pilot is not sitting on board with gauges and system status displays in front of them, the system needs to send this information to the operator on the ground. Fortunately, the Cube Pilot hardware and software facilitate this quite readily using the Mavlink protocol, which can be transmitted wirelessly to the ground to be displayed on a ground station tablet or laptop, as well as the pilot's transmitter screen itself. On the subject of wireless transmission, suffice it to say, this aircraft has more than one wireless radio system in the plan. It actually will have up to 5, which can get rather complex from an RF standpoint. It will have 1 to 2 receiving and 2 to 3 transmitting radios. For the main pilot control, a 915 MHz digital system is in the design. It will carry all stick, switch, and dial inputs from the pilot radio transmitter to the aircraft, as well as the low-power downlink channel for Mavlink telemetry data directly to the pilot transmitter for display on its built-in LCD. The main telemetry radio on board will transmit at 433 MHz and is essentially a wireless serial bus. The telemetry receiver on the ground has a USB cable for connectivity to the tablet or laptop ground station, which runs the Ardupilot mission planner or an app called Q Ground Control. The aircraft will also have an analog FPV video system allowing the pilot to have an always front-facing view from the aircraft independent of what the camera operator is doing with the camera payload underneath the drone. The FPV video transmitter will operate at 5.8 GHz or 2.4 GHz depending on the situation. It can also be completely turned off if the need arises. The camera system payload will also have its own video transmission downlink. Those systems typically transmit digital HD video in the 5.8 GHz bands as well. As we go through the details of each section of the system, we will reference the systems diagram to help tie it all together. Many similarities can be noted when comparing the Roku avionics diagram to the Cube Pilot ecosystem map. As with most multi-rotor aircraft of any size, the motors are brushless. I am only skimming the surface of brushless motors motor operational theory here, but most brushless motors in this category are three-phase motors, which require some form of driver circuitry to modulate current into the stator windings and advance the permanent magnets in the rotor around the stator. The driver circuit is referred to as the ESC and typically consists of a microcontroller to accept the control signal from the flight controller and then translate that control signal to a timing sequence for high-powered MOSFET transistor chips that do the actual hard work of switching power on and off to the motor windings. ESCs use some clever methods to detect the rotation of the motor in order to keep the drive current firing around the windings in perfect synchronization. The X8's implementation of this is known as FOC, or Field Orientation Control. The X8 motors are 80mm diameter outrunners, meaning the rotor is basically a cylinder with permanent magnets lining the inside of its wall. The 8X's 20mm stator and windings are fixed in place to the bottom mounting plate and make up the core of the motor. Another aspect of the X8 motors worth mentioning is that they are 100 kV. kV is a kind of roundabout way of measuring the electromechanical relationship between a brushless motor's input voltage and maximum output rotational rate. 100 kV means they produce around 100 RPM per volt at maximum voltage. So 100 times 50 puts these motors in around the 5,000 RPM max range, which for 78cm propellers results in a tip speed of over 733 kilometers per hour. Speaking of propellers, the 30-inch props that are part of the X8 propulsion system have folding composite blades on aluminum hub brackets. The prop spec is considered 3090 or 30 by 9, the diameter being 30 inches and 9 signifies the pitch. I'll put a link in the description that explains prop pitch spec, but in short, the pitch number means that in a perfect fluid, the prop will advance the distance in the direction of its shaft axis per rotation, in this case 9 inches per rotation. As mentioned a little bit ago, the Hobbywing X-Rotor Pro X8 is a 12S system, and if you aren't familiar with the 12S term, it means it is designed to use batteries that have 12 3.7 volt lithium polymer cells in series. I've included links in the description that will explain lithium polymer battery configurations in more detail, including a video from Bruce Simpson, who has 2 of the longest running radio-controlled aviation YouTube channels. 12S is often referred to as a 50-volt system, as at full charge of 4.2 volts per cell, the series battery pack has 50.4 volts DC on its terminals. A requirement I put on the list of the Roku design was for it to be able to accommodate several different battery configurations, whether using pairs of 6S batteries in series or pre-made 12S batteries. Having flexibility is important to be able to accommodate different payload types while keeping the all-up weight in spec. All-up weight is the total weight of the system, airframe, payload, and fuel, which in this case are the batteries. Roku will be tested with sets of Tattu 6S 14,000 mAh packs in series that are already on hand here in the shop. However, it will be able to fly with a variety of capacities tailored to what the payload weight is for a given job and how long the flight time needs to be. There are definitely trade-offs here, and it will always be a balancing act. Charging batteries of this size and voltage is a process that must be done with great care. I've been using iChargers for some time with modified server power supplies to provide the 25 to 26 volts DC to those chargers. The i406 Duo is a 2-channel charger that can deliver a total of 40 amps of charging capacity for 6S batteries. The 406 is able to charge the pair of 14,000 mAh 6S packs discharged to about 40%, back up to 100% in about 30 to 40 minutes. It seems like an afterthought kind of subject, but power distribution on an aircraft of this magnitude is a big deal. The amount of electrical current that will flow from the batteries to the motors can reach several hundred amps at 50 volts DC. Here is a graph. Based on the X8 motor specs, you can see that at 100% throttle, the motors will be pulling nearly 400 amps at 50 volts. That's in the realm of 20 kilowatts, which is likely more than your home or apartment is using right now, unless you have electric heat or charging your electric vehicle. To handle this level of electrical current, you need pretty serious power distribution gear. Having built my own power distribution for previous heavy lift multi-rotors, I briefly looked into doing the same for Roku. However, upon discovering Mouch Electronics, it quickly became apparent that their flagship model 031 of the PC series was a perfect fit for Roku. The 031 has dual 200 amp Hall effect current sensors, a solid state main switch, as well as redundant voltage regulators to power the flight controller and other critical avionics Avionics units. The main switch allows the aircraft avionics system to be powered up safely when the batteries are connected without applying power to the main propulsion motors. The solid-state main switch is enabled using a push button that will be mounted on the airframe. There is also a power tap that comes before the main switch for powering any other non-motor systems as well. This tap will be powering another Mouch Electronics module, a PC2 voltage regulator, and it will take care of powering the FPV Video, Telemetry OSD, and other future subsystems like lighting. It will also feed a side panel with power taps to power gimbal and camera systems if they do not have their own power source. I am planning an in-depth review of the Mouch power gear that will be in a separate video. Okay, let's get back into the avionics. The single most important piece of the drone is probably the flight controller, which really is the brain of the aircraft. CubePilot comes in many colors, of which the orange model made most sense for Roku. Cube Orange uses an STM32H753, more commonly referred to as an H7 processor, which contains a 480 MHz ARM Cortex M7 CPU. This main chip is the core processor of the flight controller and also has the primary I/O for serial bus protocols including SPI, I2C, CAN bus, UART, as well as analog to digital converter inputs. The Cube Orange also incorporates a second I/O chip for communication buses such as additional PWM channels, S-Bus I/O, and other peripherals such as onboard status LEDs and an optional safety switch. One of the main functions of a flight controller is being able to sense the movement and orientation of whatever it is attached to. This is accomplished by what is known as an IMU, or an inertial measurement unit. An IMU by definition is a combination of sensors to determine a body's orientation and changes in movement. They typically consist of gyroscopes, accelerometers, and sometimes a magnetometer. IMU technology has been around for some time, the first ones being mechanical in nature. They consisted of spinning gyroscopes and weight-based accelerometers that took up a lot of space and weighed more than Roku will, fully loaded. Aviation and spaceflight started out by using these mechanical types of IMUs to assist in early flight control and autopilot systems. Fast forward to today, where we have incredibly miniaturized this technology. The R&D that went into what led to smartphone and mobile devices and the subsequent mass manufacturing of their components has greatly benefited many other industries, including this one: unhumaned autonomous flight. MEMS-based IMUs are a major component of both handheld computing as well as flight controllers like the CubePilot and many others. A 6-axis IMU consisting of a 3-axis gyro and a 3-axis accelerometer with staggering accuracy can be fit into a hilariously small silicon chip package. Many also include a 3-axis magnetometer acting as a compass used for sensing the body's heading in any orientation with relation to magnetic north. The Cube Orange has 3 internal IMUs. 2 of the 3 onboard IMUs are on a vibration-isolated and temperature-controlled PCB inside the Cube housing. One is a 6-axis module and the other is a 9-axis. The third IMU is a 6-axis chip on the main Cube FMU board. All 3 IMUs are connected to the main STM32H7 chip via high-speed SPI ports. All 3 are manufactured by TDK and Vensense and come from the ICM line of chips. The Cube Orange also has twin internal barometric altimeters, which calculate altitude based on air pressure. One is on the isolated IMU board and the other is on the main FMU board. Both of them are the MS5611 series part manufactured by TE Connectivity. I had originally selected the HERE2 model GNSS for Roku. However, during the design phase, the next generation HERE3 was announced. Coupled with a Tau glass patch antenna, the HERE3 uses the higher precision U-Blox M8P GNSS module capable of simultaneously accessing 2 available positioning system constellations, including the United States GPS, China's BeiDou, and Russia's GLONASS. The HERE3 module also has its own STM F3 processor and a TDK and Vensense IMU and baro altimeter. All of a HERE3 module's sensor data is processed by its F3 chip and is accessed via a CAN bus connection back to the flight controller. Roku will have a trio of HERE3 modules for accuracy and redundancy. The Cube Orange will ingest all of the sensor data, both from its internal and external IMUs, magnetometers, as well as the 3 GNSS positioning antennas, and use algorithms to determine an accurate position reliably. I just mentioned SPI a bit ago, which is a great segue into talking about the other connectivity that Cube Orange has to offer. Along with SPI, or Serial Peripheral Interface, The STM-H7FMU chip has several other types of I/O protocol ports for connections of all matter of sensors and other peripherals. 2 I2C buses, 2 CAN buses, 6 serial UART ports, as well as 2 analog to digital converter ports are present directly on the H7 FMU. It also has 6 PWM ports that can provide connectivity for devices like servos. The software the Cube-Pilot Orange runs is Ardupilot 4.0, which has been in development as an open source project since 2009. It was originally written for the Atmega-based Arduino, hence the Ardu part in the name, but it has had significant rewrite into native C++ to take advantage of more powerful processors like the H7. There are 2 main applications available for configuration and mission planning of an Ardupilot-based flight controller. Ardupilot Mission Planner is the primary app, and there is also Q Ground Control. QGC has a user interface that is a bit cleaner, but does not offer all of the advanced configuration and functionality that Mission Planner does. I will likely use a combination of both applications to configure and fly Roku. On an aircraft this size, it's a necessity to have telemetry or live data streams of every subsystem. Ardupilot software and the Cube-Pilot hardware can send loads of real-time data from the positioning systems as well as power distribution information like voltage and current draw via the Mavlink protocol. The Mavlink protocol can be sent to a ground station for monitoring by the pilot and ground operators over a data radio. This radio can be a dedicated system or sent along with the main control radio if it supports it. Roku will have a dedicated 433 MHz telemetry data radio, and we will also attempt to send a redundant Mavlink feed with the RC system. The actual radio control system will be a 915 MHz digital crossfire system by Team Black Sheep using their Nano Diversity RX receiver. The pilot's flight control stick inputs as well as flight mode switches from the RC transmitter will be sent over an S-Bus serial link to the Cube Orange. This brings us to video systems. This area can be rife with nuance and complexity due to the wide variance in the way video signals can be transmitted. Considering Roku's many possible uses, the key is having flexibility. What works in one situation may not work for another. Since it is very likely that at least 2 video transmission systems will be used simultaneously, management of the frequency bands as well as the power outputs must be done with care to ensure optimal performance. As mentioned in the intro, an always front-facing servo-tilting FPV camera has been incorporated into the design, as it has proven to be a great asset as it assists in keeping tabs on the orientation of the vehicle in flight. The servo will allow it to tilt its pitch anywhere from 15 degrees up to greater than 90 degrees down, which will allow for aligning the aircraft over objects on the ground as well as for viewing the payload when underneath. This will be an analog system using a CCD or CMOS sensor FPV camera coupled with a Mavlink OSD module and a TBS Unified 5.8 GHz video transmitter. The OSD generator will overlay real-time telemetry information from the flight controller's Mavlink protocol onto the FPV video feed for transmission to the ground station. The main camera payload may also use a 5.8 GHz digital HD transmission system and could be very sensitive to interference from the onboard analog FPV transmitter. So the ability to change the video transmitter out to use a different frequency band like 2.4 GHz is part of the planned modular design for the onboard video tray. A fair amount of time has been spent in Fusion 360 working through various methods of mounting the power and avionics components in the airframe, with a focus on the balance between cable management and airflow. There are 6 system trays that fit between the arm root brackets in the airframe. Since I have 3D printing capabilities here in the shop, it was a logical choice to just export the tray components from Fusion 360 and slice them for printing. PETG or PETG was selected as the plastic filament type as it has a lot of the same strength benefits of ABS, but it holds up better to the UV light of the sun. The rearmost tray is home to the 4 XT90 battery connectors and the main Mouch 031 power distribution module. With all of the electronic and electrical system components contained inside the airframe, consistent airflow will be needed to prevent heat buildup. I've modeled a place for a 40mm exhaust fan into this rear tray between the battery connectors. The front tray holds the servo-actuated FPV camera and its OSD module, as well as the FPV video transmitters. This one was fun to design in Fusion and then print. It only took a few revisions to get the geometry right. The other front trays have ventilation intake slots, and the right front tray will be home to the RC receiver. The left tray has the flight controller I/O, the 433 MHz telemetry radio, as well as the main power arming button that controls the Mouch-031. A 128 by 64 pixel OLED screen will also display the status of the flight controller. The right rear tray is home to the accessory power output jacks. I found some nice looking LED segment voltmeter displays that will show the output voltages of each set of XT jacks. From left to right is the full 12S 50.4 volts DC on an XT90 with the white voltmeter display, followed by 6S 25.2 volts DC on an XT90 with the yellow voltmeter. Then 12 volts DC will be available on XT60 connectors with the green voltmeter, and 5 volts DC on XT30s with the red voltmeter display. This look of course appeals to my love of 80s sci-fi, as it kind of looks like the time circuit displays from Doc Brown's DeLorean time machine. An elevated central tray will be home to the Cube Orange and its carrier board, as well as any other modules that need a place to live close to the Cube. Motor power wires will route underneath this tray to connect to the Mouch-031 PDU. It's pretty clear that avionics and power systems are complex subjects on any remote operated vehicle, and even more so when we are talking about a heavy lift drone with autonomous capabilities. There will likely be several changes along the way during the system's integration, which is expected given the nature of the prototyping process for a complex system. I've actually made some initial progress on the frame build, which will be the focus of the next couple videos in this series. If you're still with me at this point in the video, I'm impressed. Consider subscribing to the channel and clicking the bell to get notified about future videos. Thanks for watching.